there is an update. Yesterday, I was speaking with John after the yesterday's session. Remember that we were discussing this kind of things here with this tower here. Um, two things, two updates. As I told you, with John Team is a small team, so they are very reactive to suggestions and implementation. I'm going to share the screen so you can see what's the updates. So yesterday we were discussing this, like bringing this parameter here, the parameter for unit price inside Revit. So, and when creating the schedules and quantity, there was a problem with the units, and this problem, well, of course, there is the Grasshopper solution, so you can calculate the cost for each floor actually, and bring it inside the instance parameters. So it's something that we can solve like this. But as I told John also, um, some users prefer to maintain everything inside Revit. So instead of producing documentation like a hybrid documentation between Grasshopper and Revit, it would be better to have this kind of information also available in Revit itself. So you can create schedules quantity directly inside the other software, and therefore he is going to implement another parameter, which is going to be something like cost price or something like that with the proper units, exactly like the measuring units like length, area, and volume. Um, the other there are other two things actually that he managed to solve on the fly. The first one is a problem that I already reported to him about the shafts. So you know that, for example, in Revit, when you have stairs connecting several stories, several floors, you can create a void volume that simply cuts a hole through every floor, basically, and therefore it allows placing the stairs correspondingly in a good way, basically. This feature was not working. Now it is. So now you can easily create shafts and voids inside the floors in Grasshopper, and they will be recognized by Revit as shafts. So it's pretty nice to have this feature. Else, it was something that you should do in Revit manually after importing the stairs that you can create in Grasshopper. And the third thing, remember yesterday we were trying to create these floors, and as I already told you, Geometry Gym tools are optimized for structural analysis somehow. And so when you create the material layer, there is no, there was no possibility to specify if a material layer was contained inside the core of the floor or up or down from the core of this floor. And actually, you see that this GG Revit material layer actually says that it's old. That's because John published already an update yesterday. So our suggestion was already received, and the problem was solved. So I don't know if you already put the new version of the Rhino 6 export for IFC tools on its website, but I can share the link with you. So let me open the chat window. So I will put this link in the chat. It's actually stored on my cloud, but you can download this file. And well, of course, you have to close Rhino Grasshopper, and then you have to install this new version of the IFC export tools from Rhino and Grasshopper. And this will create a new version of this Revit material layer. So actually, if I go here in Revit and grab the material layer, you see that it's slightly different from the previous one. He added this core input. And so when this core is set to true, it means that the Revit material layer belongs to the core. While if it's false, it is either up from the core or down from the core. It depends on in which order you plug the wires inside the layers in the Revit floor type, as we saw yesterday. But we will run through this again, so we are going to see this in action. Okay, so these are the three updates. As you can see, it's pretty fast. John is pretty reactive on this. He struggles to keep the plugin well up to date and also efficient. So I still think also for this reason that well, actually, there was an email from one of the participants, Roberto. He was asking for what about other interoperability tools that well there are plenty of them. Actually, I think that I also have others. I don't even remember. Sorry for this, but I think I had at least another one, unless I removed it, which is possible, by the way. Um, yeah, I think I deleted this the other option. This is the other toolbar from Geometry Gym, which is called Boolean. It contains some utilities and some things that eventually we are going to see some of them. Yeah, we are going to see some of them with the next exercise that we are going to do. IV. This is Lunchbox. You know probably this plugin because it's a pretty interesting plugin. It has many nice features like paneling, but also machine learning tools, which are quite nice to play with. But also the author of Lunchbox, which is Nathan, he created also another plugin which is called Conveyor. Conveyor is another plugin that allows interoperability between Rhino, Grasshopper, and Revit, which is a good choice actually. Um, but there are plenty of plugins. If you browse, for example, on Food for Rhino, you will find several plugins for Rhino, Grasshopper, Revit interoperability. But most of them concentrate on. Yes, by the way, I think I deleted everything. Most of them concentrate on the geometric aspect. Okay, so uh, so basically you can get some geometry exported from Grasshopper, imported inside Revit, also with a decent level of interactivity also. So you just press a button and you see that things update more or less in real time. But when it comes to defining all the parameters that you have inside Revit, in my opinion, Geometry Gym is still one of the best options. So that's why we are focusing on this tool. Um, I don't know if there are questions or doubts about what we saw yesterday before we start with the updated material layer. Just to give it a look, it's pretty straightforward. We are not going to waste too much time with this. Then we are going to skip to the next exercise, which is going to be a little more intense, I have to say, because it will be a multi-story building, but with some details, and not just like this tower, which was good to start understanding what are the features of the Geometry Gym plugins. Well, okay, so let's jump into today's session. I'm going to quickly go through this new material layer. So nice to be part of the development of these tools. Yes, basically we must substitute this old material layer with a new one. I do recommend that you install the new version of the Rhino IFC, Rhino 6 IFC exporter. So the link, I don't know, because normally what happens in Zoom is that if someone connects after I've published something in the chat, then he or she cannot see the old messages. So this is basically the links that you need to download the updated version. But I think it's already available on his website. They are pretty efficient in this. But anyway, so yeah, we have an additional input basically. Um, the other thing that I would recommend also would be to, as far as possible, if you are keen to create a default workshop in your a standard workshop in your office or whatever, I do recommend that you create a Grasshopper template made for creating this kind of uh, export process. It, the more efficient is the template, the quicker and the let's say less effort you will have to do in order to create the proper architectural element to be transferred to Revit architecture. So for example, I refer to these names here. My floor upper finish, uh, well, basically it's going to be received by Revit. So this material is going to be created. It will be present in the material library, but it has no attributes. It has no physical meaning. Okay, not even as regards to representation and visualization. So you have to build this material from scratch once you are inside Revit. Of course, if you define this name here in Grasshopper and you import it inside Revit, and you are importing inside Revit into a file which depends from a template that already contains this kind of material with all the corresponding properties, you can use my floor upper finish. But it would be better to create here something like a value list, like, for example, something like this. You can name this Revit material. And here, for example, you can use, I don't know, ceramic tile, which is, oh, sorry, I think this is going to be the name. So Revit material, then you go inside here and you say ceramic tile is going to be material number 0. Of course, it doesn't matter if you give another value to this name. You just remember that this is going to be the material that you want to use. Okay, or better in this case, as we are not going to make some selections, we are going to define just the name via a text. So here inside, you can also specify that the value is exactly the same. So you need to specify a text and you write it down like this. So once you select ceramic tile, you will have this text here. Remember to put it inside. I don't remember the English word for this. But anyway, you get the point. Okay. So in this case, you can create a comprehensive list of the Revit material. Remember that if you want this process to be efficient somehow, let me grab the architectural template that I created. And here inside, when you create, well, basically whatever. Okay, so, oh, this is a structural column. That's why it's a Revit create that warning here. So the column lies below the level 1 floor. This is something that eventually you should know already. Oh, sorry. No, I didn't want to create a column. I wanted to create a wall. So let me create a whatever wall you might want to create. When you go into edit type and you have a structure and you have this thing, you can create, for example, another material. Let's take this and eventually place it on top. Let's give this a finish material, and the material is here. You can see there is a whole set of materials inside the standard Revit template. And one of those materials should be ceramic tile. So ceramic tile has a set of features like color in the shaded viewport and surface pattern when you want to display this material on a plan view. For example, a floor plan, you will have this kind of pattern here, like square texture applied. Cut pattern, what you see when you are in a cross section. So this is the visualization, the graphics associated to that material. Okay. Then there is identity with all the features like the parameters that you can define, and there are also physical and thermal properties. So these are the things that Revit or, for example, also other tools from Autodesk use for creating like energy efficiency or scheduled quantity if you want to stay inside the Revit architecture and so on. Okay, so if you create in Grasshopper you create this kind of value list with the correspondent name. Once you import this layer, this material layer from a floor that you are creating in Geometry Gym tools, then here, when you import it in Revit, you will have exactly this material with these properties here. Okay, so it's worth the effort. Try to create this kind of comprehensive list of Revit material. It's going to be very boring. Okay, so normally, for example, when I used to be an advisor for architectural and engineering studios in Italy, one of the main things was to have a BIM manager inside the studio. Actually, two. I do recommend to have two persons capable of doing the same job, because a BIM manager is basically a fundamental figure inside the studio. And those are the ones that are basically in charge of creating this kind of material. So they do the boring part, actually. And it's worth the effort creating this kind of elements in Grasshopper if you want to work with this interoperability workflow between Grasshopper and Revit. So there is the function. Remember to define the function properly. So in this case, I was creating another value list. Oh, I think I was making some confusion between the Revit material and the material layer. Yes, one second, Pepe. Then there is the core parameter. So if I want the upper finish, of course, it's not going to be part of the core. So I can plug this here, set this to false, and that's it. So now I know that if I plug, for example, this material layer as the first layer in my floor type, it will be the upper layer in the floor type, and it is going to be outside from the core, and it's going to be the upper finish layer. Okay. Then the structural toggle, another toggle that we must plug here. Of course, this is not going to be a structural layer, and that's pretty it. Okay. And so we can substitute the old material layer with a new one. Once you change everything here inside, let me double check if I already changed this in the actual exercise that we are going to do. No, I didn't do this, so we are going to do this in the new exercise. So just keep in mind that you have this new capability for the Revit material layers. Okay, so I'm going to turn this off because it's time to move on and concentrate on this. This is going to be today's exercise. So as soon as I turn on the preview, you will see that it's quite pretty, well, it's not complex, of course, it's, in terms of geometry and in terms of shape, of course, it's not complex. Maybe yesterday's tower was way more complex than this, but it's quite rich in terms of details. There are also some things that are turned off by default in this model. Let me get rid of the group because it's going to be easier to handle the different aspect of these things. There are some things that are turned off, and there are some red notes here that you can see. These are my messages to Geometry Gym and in John in particular. So every time I have some trouble with something, I do send this feedback to Geometry Gym, and it's pretty fast in answering the questions. So what we have here is a standard multi-story building made up of linear elements, only linear elements. Everything here is linear, like columns, beams, different types of beams actually, floors, stairs, railings, and so on. There are also some walls definition. Actually, I'm going to also show you what happens when you want to place walls here. So you see that you can also create this kind of elements automatically. Let me turn this off. Let's concentrate on the main parts of this. There is also a fancy roof that I added in order to explore other possibilities that we have. So you see there are some trusses here holding up a roof, a curved roof that you can create and export to Revit. But eventually we will take a look at this later on. And everything is basically subdivided by, well, element type or category or whatever. everyone has its own workflow and standards. But as always, you see that where you see these green groups here, it means that this is something that can be exported to Revit. It's the final step of Geometry Genie workflow. So in this case, these are the railings, and here we have the stairs. Here we have the girders, so the principal beams. These are the joists, so secondary beams. I also implemented something that we are going to see. You see that the orientation of these joists here is different from this one. So you see these are oriented like this, and these are oriented the other way. We will take a look at this later on. Then there are the columns, and here are the floors. The floors with the shaft that I was saying, it has been solved by John recently. So now we can create the stairs and also place the shaft, so you have these holes corresponding to stair position. Of course, it takes a little time to implement this kind of automatic design process in Grasshopper. So you see that this definition is quite intricate, but in the end, it's something that you will never, let's say, go back and check what happens inside this group. You're only interested in the main parameters and eventually the results. So once you define these properly, you will have an automatic process that you can simply tweak by editing some sliders or whatever. Okay. So let's see how this thing works. Of course, we have some grid lines, which is some basic stuff. I'm not going to go through this anymore. Just remember that this tag asks for visualization here in Grasshopper, okay? But you don't need them actually. Also remember one thing, which can be important. The labels that you are plugging here, so the grid name follows the sequence order. So it's always going to be A, B, C, D, or 1, 2, 3, 4. Okay. It's important to give this Revit grid element, this Revit grid component, the correspondent lines in the same order. So if you want, for example, like A, B, C, D to start from the left to the right, these lines must be in this order. Okay. Else you are going to get some weird result in terms of labels and tags. Okay, so I'm going to turn off the grid elements, and then let's concentrate on our model. I'm also going to turn off all these elements here. So Control Q, and the stairs, and also these columns. Okay, so let's go step by step. I'm not going to recreate this from scratch because it's quite an effort, and it could be boring for you. But eventually, at some particular point, I will be describing the process analytically, so it would be easier to understand. So first thing first, levels. Well, actually, the grid itself is somehow important. You will see this later on. But first thing, the levels. One consideration about the levels is the naming. So as Soto was saying, there are some things that you must consider when you export these kind of entities from Grasshopper to Revit. For example, if you open any Revit template, you will see that by default you already have two levels. Okay, so and level 1 is basically the ground floor, so it's 0.00 meters, and level 2 is 4 meters. Okay, so you already have level 1 and level 2. What happens here in Grasshopper? We are defining levels starting from level 0, which lies at the height of 0 meters, and then level 1, which already exists in Revit, and it has a height of 0, and level 2, which is going to have a height of 7 meters, is going to be this one, okay? While in Revit it already exists and it has a height of 4 meters. And then there is level 3, which will have something like 10.5, and it's not existing here in Revit. Okay, so there is already some kind of interaction, you know, from elements that you are sending from Grasshopper and that already exists in Revit with another property like the height, or they don't exist and they are going to be created during the import process. So what happens with levels? If you go inside Revit and go into Geometry Gene and import IFC, and you select whatever IFC file, you have this window here. You see that there is an option here that says update existing Revit level elevation. Okay, so this means if you leave this, of course, active, when Revit finds that another level 1 is coming in, it will change actual level 1 height with the new level 1 height. So this is important to leave this active when you import, for example, levels from Grasshopper. So this will avoid any type of mistake when you create this kind of interaction. So levels start from level 0 for us, and they're going to have a 0, 3.5, 7, and 10.5 height. Okay, and that's it. That's the only consideration. Column access. Now we have grid lines. Okay, we have grid lines. We want to place a column at each intersection between these grid lines. That's the way that you also do things in Revit. So for those who are not familiar or used to work with Revit, there is one simple recommendation that I always give in my Revit courses, which is always start like if you were building something. So if you're on site and you want to place columns, first thing that you do is you trace lines, structural lines or grid lines, reference lines, whatever you want to call them. Okay. So here in Revit, try to maintain the same workflow. Well, actually, the first step should be to create the site properties or site characteristics, like the topo surface or whatever, and then you switch to the architectural phase or structural phase, which would be more appropriate. But anyway, let's keep this like an architectural workflow. So you go and place grid lines, okay? And so this is the first step. You place grid lines, however you want to place them. And once you have the grid lines, you can place columns, like, for example, you see that structural columns in Revit are subdivided between structural and architectural column. This is something that it's very important to understand. Architectural columns are fancy objects that are only needed to give finishes to structural column and to interact with vertical elements like walls. Okay, so this is in general. The standard process, if you think about building something, you first create a structural column and then you make some operation that gives this column some finish or something like that. This is the architectural part of the column. Okay, so think about the columns like in this sense. So you see that, for example, placing structural column has some kind of automatic properties, like place columns at grid intersection. So you select the grid lines, and then when you finish, Revit is saying basically that as you are placing structural column, they are invisible at level 1, because structural column, from a structural point of view, the columns are bearing the actual level. So you will find them at the lowest level in this case. So they are bearing level 1. They are not starting from level 1. That's what happens when you place structural columns. Okay. So a structural column visible in level 1 will be a structural column for a level 2. Okay, that this is the way that structural engineer understand columns. Okay, so you see that placing structural columns as this kind of automatic process, like selecting the intersection between the grid lines, and this is something that we must do also here in Grasshopper. Okay, so all this block here is actually calculating these intersections. So you see that, for example, this is the main component. It is actually taking the two sets of lines that I have created manually here in Rhino. Of course, you can create these initial lines, initial curves with whatever method you might want to use. Okay, you can create a grid, you can create whatever. But if you want to have a quick approach to creating grid lines, I do recommend that you do this like this, like creating by hand the original lines, or drawing them in Rhino and then importing them in Grasshopper. Because in this case, for example, you might notice that this is not a square grid. Like these six parts here are square, but these are rectangular. Okay, so if you want to create this, you can not use a standard grid component. It would be very interesting, for example, to explore something like application of um, plugins like what is it? Yeah, like paneling tools, which is capable of handling the grids in a very efficient way in order to create also some strange or non-linear or non-usual grids. Okay, but this is something for further exploration and further also for fun somehow, because in the real life, if you want to build something like complex, it has some cost problem. But anyway, you take these two sets of line and you calculate the intersection, which are physical intersections. So once again, you're going to intersect physical, and you will find curve. Remember, you must graft at least one, well, not at least one of the two inputs in order to create the whole set of intersection. If you don't do this, you will have some intersection like one line with one line, then second line with second line, and you will have only this diagonal intersection. So that's why there is this graph here. So these are the intersections. These intersections are going to be considered like the starting point for these SDL lines. And these SDL lines, they all share the same length, which is basically the level height, you see, minus, this is the other parameter that is going to be, that is taken into account for creating these columns, which is the thickness for the floors. So you see that actually these lines are stopping below the floor. Now, it depends on how you want to build this structure. Of course, this is something I'm considering here, that there would be beams here, and these beams are going to hold this floor here. Okay. Of course, you must also assure structural continuity, but it's just to implement a workflow with several parameters. Okay, so don't take these as the correct structural solution. It's just to have the idea that if you want to interconnect, for example, one architectural element with others, you must create this kind of connections. Like I'm connecting here the resulting thickness, which is this one, with the actual level height. Okay, and so we have these lines, and these lines are going to be used as axis for our columns. Okay, so this is the axis, the line definition for the columns. Here is another approach. You see that this is actually disconnected. There is nothing connected to this final component. In this case, I was referring to the floor creation, but you can also use another method. In this case, I am considering, for example, the frames. You see, this is not actually the level itself. You see that we have here a line that connects from the bottom of the building to the roof, to the top. Then there is a divide by length, which is actually using the number of stories that you want to have. So it's dividing this by length, and then you have these points. You place the frames. You select the frame that you want, which is actually the first layer, the first level, and then you create an intersection between a longer or an SDL line and the correspondent frame that you want to use to stop the column axis. So it's another process. I mean, it's something that it's actually disconnected. So if we get rid of this, nothing happens inside our definition, okay, because it is not connected. I will leave it here like an alternative way of defining this column axis, okay? But just so that you have an idea of why this thing is here. And of course, as we were saying yesterday, there are other alternatives that you might want to consider. Of course, they are not going to work with this example because this example is built to work with this vertical axis, but this is actually, for example, a vector XYZ, which is a custom vector. If you want to see this vector display, I'm going to anchor this at the XY plane. So like here, so we can see this. What's the orientation of this? You see, it has some inclination, but you can change this with using these values. So you see that we are defining the inclination of this, the orientation of this vector, and you can use this as the direction for your SDL lines. Of course, this is not going to work for us in this case, but this is an alternative that you have. And the other one that we already saw yesterday is the attractor. So if you have an attractor somewhere in your definition, then you can use these vectors to orient the columns towards the attractor. Okay, so here, once again, when you see these gray blocks here, it means that you have alternatives. Now let me disconnect the vector. You have alternatives to the actual configuration, but they might be useless in the general process. Okay, so let's move on. Let's go into Revit columns. You see that one of the things that I have noticed, well, two things about columns. First one, they are not set to be used as architectural column at the moment. So this is another feature that is going to be implemented that probably is going to be published pretty soon. So there will be an option for creating architectural columns. And there is also a little problem with the columns are created and imported correctly. So you have them available in your architectural model in Revit with no problem. The only problem you get is the association between the column and the proper level. So for example, you see that these columns here start from level 0 and are basically ending at level 1, okay? But when you export the columns and you import them inside Revit, it might happen that your column, for example, belongs to level 1 with an offset for the starting point of minus 3.5 and an offset from level 2 of minus 3.5 again. So it's like this column belongs to level 1 with an offset of minus 3.5 that brings the column to level 0. So it's basically something that of course is not correct. John is already aware of this and is going to take a look at this soon. So be confident that this is going to be solved pretty soon. But anyway, that's why you see this red note here. Here is the standard process that we already know about columns. There is here a linear array because I want to define columns for each level, of course. Let me get rid of these previous lines. So yes, these are the actual column axis, one for each story level. So you see that this is x minus 1 because if you want to have 1, 2, 3, 4 levels, but you want the columns only between the ground floor, first floor, second floor, third floor, and not upstairs, then you must reduce the amount of repetition for this linear array, which is vertical, by the way, and has the factor, which is the layer, the level height. So these are the profiles. You can use catalog profile, as in this case, you see that this is the one that's connected, but you can also use a custom profile like for defining this column type. One consideration, and remembering the question from yesterday, one of the questions from yesterday, if you define column with this standard profile with these parameters, you can also use the same definition to structurally optimize the columns before sending them to Revit. So I don't know if you're familiar with this, but you can use some optimization processes in Grasshopper to connect it to some structural plugin, like for example, Caramba 3D, which is around here, is one of the keys that we have. Yeah, this one. So in this case, for example, you can run this optimization by optimizing the various parameters of this section in order for this structure to work, basically. And once you run the optimization, then you can export to Revit. So you will have also a pre-calculation made on the structure that you are exporting. Of course, when you export an IFC, we are using the Revit tool from Geometry G. So this one. But there are also other tools that can export to GSA, Robot, or whatever software. And also, they also advertise that if you are using some particular structural calculation software, you can tell them, and they are going to also connect Rhino Grasshopper to that particular software via IFC. So it's pretty open as possibilities. But yes, that's the reason why you might want to define this profile by hand or with parameters. Okay. Of course, well, this is something that we must tweak. This is, of course, this is going to be a structural column, but this is an attempt that I was doing before I spoke with John in order to obtain some architectural column. So I was supposing the structural was meaning the opposite of architectural, but it's not like that. So that's why you see these faults, but this is actually a structural column. So you must turn this on. Structural columns are basically visible in the structural template in Revit viewports. But we will take a look at this soon after we export this model to Revit. And then the usual parameters, attributes, the name of this column, which is actually not given. When you don't give a name to a column type, the name will be basically derived from the profile. So that's why there is no name for this column type. And this is normal for columns. Basically, you recognize a column, a structural column, by its profile. And then there is the Revit column. You see this thing here, this weird thing here. This is an attempt of changing the material for only one of the column or some of the columns. So it's a replace items, a standard Grasshopper component from sets manipulation. So you grab the list of material, and then you substitute at index 5 of each branch of this data tree here. You substitute the actual material with another material. Of course, not chow. You must build another material and plug it into item. And then eventually you take the output of this and plug it inside the Revit material for the instances in this case. Okay, so the actual column type will have the proper material, which is going to be only this one. But if you want to change the material for some of the columns, you can use this method here and plug this inside the Revit material for the Revit column instance, not type. Okay. But anyway, this is something that if you want, just before exporting, this is a panel showing us all the instances that are going to be created by this element here. If I plug this inside the Revit material, you will see that at a certain point, let me double check if everything is working properly. Yeah, you see that there is this IFC material, which is coming from the type, and then there is chow. Okay, so the thing with instances is that not all the parameters are visible inside the instance, because they are basically a set of strings or symbols that tell Revit how this instance is going to work. But nevertheless, remember that if you do this, you are substituting the material for some of the columns, okay, corresponding to these indices here. This might be useful. The only consideration should be to identify or distribute the columns in the proper way in order to make this operation possible, because it's quite difficult to isolate exactly that precise column once you have the data sorted in Grasshopper in a particular order inside the list. Okay, so that's the only complication that I see for this process. I'm going to disconnect this, so it's going to use a uniform set of materials, which is going to be the material for the column type. Here there are some attempts that I was doing, because remember of the problems that I was saying. The columns, like in this export here, will belong to Revit levels in a weird way somehow. So you might have this column belonging to level 1 instead of level 0. And this was an attempt that you can do in order to assign a specific element to a specific host. So I was trying here, there is a component in GG Revit generic commands, which is called Revit set host. Okay, like this one. It asks for the element and for the host. So the idea was that, of course, it's not working. The idea was to take the elements, like the columns in this case, the columns instances in this case, use them as element for setting their host, and then go back to our levels, which are these ones. You see, there are 0, 1, 2, and 3, and use them in order to use them as hosts for the different elements. Now, considering that these columns are subdivided into 3 branches, so 16 columns per level, basically, excluding the level number 4, which has no columns, as you can see. What I did here was take the list of levels, eliminate the last level. So in order to have here, you should see that we only have from level 0 to 2. Let's see, level, well, okay. So we have level 1, level 2, level 3. Actually, I think that this is not correct because the first level is level 0. So I should have, maybe this is the error that I was doing. So I am taking the number of stories, eliminating 1. So from 0 to 3. No, this is not correct. This is not correct because I am creating a domain which is not correct. So if we have, so the idea is to grab this list of levels and just consider level 0, 1, and 2, which correspond to indices number 0, 1, and 2. So I made a mistake here. So let me correct this. I only need from index 0 to index number 2. So the main start is not 1. The main start should be by default 0. And the main end should be the number of floors, basically -2 in this case. So not 1. So what I should have here is level 1, level 0, 1, and 2. So I'm then grafting this because I have 3 branches for the columns, and I need 3 branches for the hosts. Okay, so this is an attempt of subdividing the columns per level. And I was doing this. It's so strange that I did this rookie mistake, but anyway, I was doing a mistake, and eventually, when we re-export this, we can double check if the columns are actually properly associated to the correspondent level. But anyway, we will double check this later on. So that's it for the columns. You see that many blocks here are interconnected because we want the specific heights, especially the heights. We want them to correspond between floors, levels, columns, and so stairs, and so on. Okay, so that's why you see these wires flowing all throughout all the canvas. The other important things are the beams. Okay, this is something that we saw yesterday. I've used the same method actually. So let me hide the columns for a while. Let me also hide the levels. Let's go back to the column axis. Okay, so you see that this is also connected to the girder block. Everything I did in this definition is defined at the ground level, the ground floor, and then it's repeated like with a linear array vertically, okay, in order to work just once. Of course, if you have changes or variation at the floor, at each floor, then you cannot work like this. All my floors will be identical, okay? So in this case, you see that I grab the endpoint for this line axis and interconnect the endpoint in order to create this grid of connections. Okay. There are several ways of creating this. Actually, you could also work with the original lines calculate intersections, because if you go, for example, inside this geometry gene tools like the bull ant tools, you will find some utilities like network polygons, for example. Network polygons is capable of recognizing the cells or the polygons that derive from the intersection of several lines. Okay, so it's easy, for example, to derive sets of girder of beams starting from this set of intersecting lines. But anyway, this is another method. I prefer to work with this because it gives you a whole range of possibilities. Okay? Of course, you have to change this parameter accordingly. In this case, yesterday, remember, there was no internal column, so there was no need for creating 4 intersections, but in this case, yes, 4 connections, sorry. And the distance is set to avoid diagonals, okay? Of course, this is not going to work like this easy if you have an extremely changing length between the grid lines. So in this case, you see that the separation between the grid lines is more or less the same, even if we have this slightly smaller separation between the first and the second grid line horizontally. But nevertheless, you see that with 5, we already got rid of the diagonals. Okay. Once you have the axes, I just repeat them again. And another reason for using incestuous network is that you only have one line per connection. So if you imagine, for example, to create this set of connection using another method, for example, creating these polygons here, you will have 2 lines overlapping here, because this is one side for this polygon here and one side for this polygon. So you will have 2 overlapping lines. And then you will have to use other tools in order to remove duplicate lines. For example, there are some tools in Kangaroo that allow to do this. These are the axes. These are the axes for the beams at the several floors, and there is the beam definition with the name, girder, Revit profile from catalog, and the material. And here we have the resulting beams with girder function. So let's turn off also this, but let's leave the incestuous network visible, because the next step is going to create the joists, so the secondary beams, basically. So you see that this incestuous network is actually connected to this curved container. So we can also start analyzing this from here. And you finally see here that I have used the GG network polygons. So actually these are a separated line, independent lines, but this is actually polygons. So you see that cells are polyline curves. They are 9 polyline curves. Okay, and from these I derive the centroid, which is basically calculating the area of these polygons. Then this thing, I did this thing because when you create this kind of incestuous network, the connection scheme doesn't follow the order of grid lines. So, for example, I'm interested in, let's say, what I want to achieve right now. Let me show you the final result. Is this thing here. So you see that inside some regions, some of these 9 regions that we have detected, joists are oriented like this in some regions, and like this in the other regions. Okay, so I want to be able of changing this orientation, and in order to do this, I must understand which region is which. So, for example, I want to sort this region like 0, 1, 2, 3, 4, 5, 6, 7, 8, you know, so something like this, in order to be able to recognize which region I'm affecting with this reorientation of the beams. Okay, so that's why here the only thing that I'm doing, which is a little tricky sometimes to do this kind of operations. So I'm going to describe this in order for you to get a glimpse of real life working with Grasshopper. So in Mexico they call this talacha, So it's not a smart work, but it's a useful work. So once you have the cells, I want to sort these cells in a reasoned way. The reason why I want to do this is because if you take the centroid of these areas and you use a tool like, well, actually, we already have this available, so I'm going to copy it from here. So you see that actually these are the properly sorted cells, 0, 1, 2, 3, 4, 5, 7, 6, 7, 8. But if I take a look at the original centroid, you see that the numbers are distributed like randomly, 0, 1, 2, 3, 4, 5, 6, 7, 8. So this depends exactly from these two aspects, the incestuous network that doesn't give any preference to the order or sorting of the connections, and also the network polygons. It only detects intersection or areas, and then just they come out as they want, basically. We must have them in the right order. So that's why I take the centroid, sort the points, which means sorting them by coordinates. So if I do this, we already have the right order. Okay, and the important thing with this sorting point is not having the center point ordered in the proper way. It's like deriving the indices for this sorting. So you see that the first point is now what was the point number 3 in the previous list of points. And then you have this indices order, like 3, 5, 7, 2, 4, 6, 0, 1, 8. And if you grab the cells and create a list item using exactly this list of indices, then these are the same rectangular regions, but they are sorted properly according to this list of points. And so you see that recalculating the centroid and applying the point list, you have exactly the right order. Okay. And what comes next? Well, actually, this is some manual operation. I took a point container and specified this set of points by setting multiple points. So the result of this operation is that, let me show you the final result again. Here are the secondary beams visible. The result of this work is that if I grab, for example, this point and move it like here, you see that the orientation of these secondary beams has changed. So you can decide what orientation do the secondary beam have per each region of this floor. Okay, how did I do this? Let's give a look. You see, this is an evaluation if the selected points lie inside or outside from each of these rectangular regions. So there is a pointing curve command which evaluates if these points fall inside of these curves. Now, as we have a list of points and also a list of curves, you must graph the curves. And so by doing this, you have a data manipulation problem. So this is, again, real life, because as I have 5 points, I am obtaining 9 branches, because these are the relationship between these points here and each of the 9 regions that we have. So just to give you an idea of what's inside this, you would see that there is a list of 0 and 2s. So this thing here means that the first point that we are analyzing, which is the first out of 5, as regards the first region, which is this one, is contained inside the first region. The second point is outside, third point is outside, fourth is outside, and fifth is outside. So of course, second, third, fourth, and fifth are outside from the first region. As regards the second region, remember that they are actually sorted like this. So the second region is going to be this one. In this case, there is no point inside that region. No point inside the third region. As regards the fourth, the second point of our list of points is inside this region. So basically, once you have this, you can mass addition these values, which means doing the addition of all the values that are inside one branch. And of course, the result is going to be 2 where you have a point and 0 when you have no points. So first region has 2, second has 0, third has 0, and then there are fourth, fifth, and sixth, which are this, this, and this, which have 2, and then 0, 0, and finally 2. So now we are able, we can detect which region contains the points that we want to use for orienting the beams. Okay, so I simply evaluated if the actual value is larger than 1. So this gives us a set of true falses. And then I'm using this. This is something that I'm not going to describe in detail. This is, once again, not a smart work. This is just for selecting things properly. So you see that here, for example, what I want to do, I want to use this definition, this part of the definition, not to isolate these one set of cells from the other set. I want to use this this rule that I've derived here in this in this part here, in order to decide whether I want to divide this region like 1 by a defined number of division, which in this case is going to be 11, 1 by 11, or in case I don't have a point, I want to divide this region 11 by 1. Okay, so that's what I'm doing right here. Okay, the way it's done, you can study this because I'm going to share this definition with you, but it's basically 2 repetitions of the actual values. So you see that here you have 11 ones, and here you have, well, sorry, 9 ones, and here you have 9 11s. And so you decide, according to this pattern here, you decide whether you want to use 1 or 11 for the U and V count. Okay, so these 2 patterns here, well, these 2 series of 1 and 11s are one the opposite of the other. So where the first list is 1 division, the other list is 11, and vice versa. And so when you flip this, you basically are deciding the orientation of the secondary beams. And so there is basically converting these 9 regions into surfaces, as you can see, and then using a standard isotrim method for creating panels inside these surfaces. And then there is this component here, edges from direction. This is something that is a recent utility that is present in the surface toolbar. This was not present in previous versions of Grasshopper. This is something new. You can basically select a B-rep and only extract the edges in one specific direction. So this is actually extracting the edges in the X direction, and this is extracting the edges in the Y direction. But of course, we have trims here. We have trimmed surfaces. So basically, when you say you want the edges in the X direction, as regards the regions that are subdivided in this orientation, you will get exactly the axis for the beams. But when the region is divided in this direction, you will have these little lines here, because they are also oriented in the X direction. So we must get rid of these small lines, as well as these small lines for those areas that must be considered only in this direction. So once you detect the X and Y edges, here there is a process for eliminating the the small lines. So we only have the large lines, as you can see. Okay, so as regards the Y orientation, we don't no longer see these small lines here in this set of lines. And as regards the X orientation, we only have the large beam axis. Okay. There is also a small data manipulation here, because you see that if I consider all the edges, actually, as I'm working with panels, consider that this is one panel. Okay, so this comes in like a B-rep in this component. So its edges is going to be this one and this one. Okay, and then comes the second panel. And so this edge here also belongs to this panel. And so this edge belongs to this and to this. So we will have a huge set of duplicated lines. Okay. Also, another thing, this edge here is not necessary for the secondary beams because this is actually the axis for the primary beam that we already have. So we don't want this line, we don't want this line here, we don't want this line here, but we don't want this line that belongs to the Y orientation. We don't want this one, okay? So we must get rid of this kind of elements. That's why we have this call index that is actually eliminating some of the connections from our sets. Basically, this is eliminating the connections that are related to the primary beams. And then here, I am, by using the curve lengths, I am getting rid of the small axis. Okay, so that's what you have finally. You see that actually the primary beams are no longer visible. And so you have this set of lines, which is basically the final thing. And then another small but important process. We didn't see it yet, but there is a stair here. And these stairs are basically in this position. So basically what I did next with the secondary beams is delete the secondary beams that lie inside the volume of the shaft, basically. Okay, so that's why you see that once I define these lines here, I also calculate their midpoint by using the point on curve. And then I evaluate if, considering the area for the stairs that I have defined elsewhere, I evaluate if those points lie inside that region, that rectangular region. And so if there is a smaller than condition, which comes out as a result, you have a true false value. And then you simply have all the secondary beams that don't fall inside the volume of the stair. Okay, so that's why I need this, this thing here. Let me get rid of the surfaces. Yeah, okay. So that's the thing here. So if I turn on the stairs again, you will see that wherever I have the stairs, there is no secondary beam present. Okay, so that's another, let's say, non-conceptual work. And then I took this and did the vertical array in order to have the beams, secondary beams oriented like this. Now, you might see here that the linear array is no longer connected to the actual framing. Okay, there is a reason for this, and this is actually that something that I was also observing in the Rhino to Revit export process via IFC. For some strange reason, the linear array it is not always working properly. So I think it depends on the way that object ID is defined using the linear array. I found out that if you copy things instead of using a linear array, for some types of elements, it worked better than the linear array. So you see that here I did, well, basically the equivalent of a linear array, which is actually creating two repetitions of each set of lines. You see that this is actually the joists or secondary beams oriented like horizontally, see? And here we have the beams or secondary beam oriented vertically. So I took those two lists of lines and created two copies, two arrays basically, once again, but with a move component and not with the vertical array of the single set of beams. So by doing this, I used also two frame definition, which are the definition for the beams. Now, this is something that we didn't see yesterday, so I'm going to go into details, but you will see that it's basically the same, exactly the same as the columns, okay? So you take the instance, take the type, you define the name, you define the profile. Of course, in this case, you are not going to use eventually something like columns, you're going to use beams. I used IP beams like the smaller profile, I think it's the smallest one, yes, IP 100, which is another time is catalog profile. But you see that in this toolbar, if you go into the Revit generic set of commands, you only have these profiles. You can use them both for columns and beams, of course. So just pick the right profile if you're going to use this profile for beam definition. Material works exactly the same. Of course, there is no need here for material layers. This is a homogeneous component, so it only needs one material. And so Revit framing type usage. This is important for frames. This is something that I didn't observe here in the girder, but usage is actually defining what type of use you are going to give to this frame. You see that there are several things, like girder and joist and purlin are, well, basically the standard uses for framings. But there is also, for example, trusses at the end, as you can see, and bracing also, like giving rigidity to systems, for example, and so on. Okay, so you must, well, actually, it's not that you can, you must define the usage for these framing elements. And so once again, I do recommend that you create a value list for this usage thing. And also another thing, let me grab this because it's less, it has less density, so it's maybe easier to see other properties for these beams. Another thing that you can do is actually define the justification. The orientation works exactly like the columns that we saw. So remember what we saw yesterday with columns. Orienting a column means orienting its cross section, and the same is here for the framing. Now, normally you don't need to orient a cross section, the cross section for a beam. So it would be something like having an IPE beam like this, something like this, and eventually pretending to reorient its cross section in order for this cross section to lie like this. But if you do something like this, you are basically compromising the efficiency and the performance of this beam, of course. Okay, so this is something that, as regard beams, unless you have very, very specific needs, it's something that you might not want to take into account. While justification, yes, justification is just the position of the cross section with relation to the axis of the beam that's defined here. So that's why I turned out the linear array component. So in this moment, justification is set to top mid. So the top midpoint of the cross section is actually coincident with the axis. But if I want to define, for example, the beams in a different way, so for example, consider that this is not actually the this axis line in our geometric workflow inside Grasshopper should correspond to the lower mid point of this beam. And so in that case, you must change justification to bottom mid. And the beams are basically appearing up from the axis. Or you might define the center axis, the mid axis for the beams, and so you have exactly mid. Okay, but in my case, I was using the top mid reference point. Okay. Another thing which is important is metering the beams, and we are going to discuss this not with this complex situation here, which requires some work, but with a simpler situation that I'm going to show you later on. Okay, so meter is basically, you see what happens here. We have this kind of weird connection where the end point of one beam reaches the start point of the other one, but there is no the intersection is not taken into account, basically. So they simply overlap and they leave this corner empty. You can meter them by cutting them diagonally automatically, but I'm going to show you this in an easier example so that you get the point. And this is the same for our joist element. You have the usage, which is in this case joist, and also in this case is joist, of course. This is important if you want to switch to structural analysis or visualization in Revit. Okay, and framing type that we already saw. So just remember to change the usage of these things. Okay, and so we have a complex set of structural elements here because we have two orders of beams, taking into account also the shaft for the stairs, which is leaving these areas empty. Okay. So, for example, in this particular case, in this particular scenario that I'm considering, um, it's important to consider where you are drawing or placing the stairs, because this is affecting also the secondary beams, of course. So let's jump to the stairs. So in order to see a particular case, because everything seems, well, despite some imperfection in the actual version of the plugins that is going to be corrected, and it's always easy to correct this kind of small misbehaviors, let's call them so. Despite this, everything works pretty smooth right now, because you have the geometric definition of an architectural element, then you define some parameters like materials and so on, and then you create exactly the precise element that you want to export to Revit. For example, floors, columns, and beams. But what happens with a stair? Because a stair is a complex object. So, and also stairs are somehow a problematic element already inside Revit. So I don't know, well, just because some of you are not so familiar with Revit, I'm going to go into level 1. Well, no, actually level 2, maybe it's a little better. And I'm going to create a simple floor without considering anything, right? This is just for creating some elements in order to see what I want to see here in Revit. So from the east elevation, we have this floor right now, or maybe it's better in this case to use a section. So I'm going to create a cross section, and I'm going to create this like horizontally. You see that it has the blue symbol. You can double click on the blue symbol here and go straight to the cross section if you want. Okay. Let me also increase the detail level. Also, if you want to have a better look to the actual element, let me also visualize the thickness of the section line. So you will have a bold line for the cross section for the sectioned element. And also let me take this floor here and change to a actual composite floor. So we have layers here. Okay. So what I want to do, I want to place a stair in this project. We can also go into level. Well, let me add a level, which is somehow important right now. So let me add a level. They have 4 meters separation. So let's go here at 4 and grab this. Okay, perfect. And so let's go to level 3. You see sort of that once you create a level here, we have automatically the floor plans and ceiling plans automatically created. So that's something that we were observing already. So you see that here, for example, as I created this level after creating all the rest of things, I don't see basically anything here. What I would do right now, just to make things easier, I would overlay or underlay, in this case, level 1 to level 3, so I can see the floors that are already present downstairs. And so let me create another floor. You can also use other method like copy pasting elements from one level to the other, but I do not recommend you do that unless you know exactly how to do this. So I'm not going to go inside Revit dynamics for now, but this is something that you might want to double check before doing copy pasting Revit. So don't copy paste things unless you know how to do this. Let's move back to the cross section. Let's expand the cross section visibility. So we have now from ground floor up to the second floor, and this is also going to be the same steel bar joist floor type. So once we are here, what I will do is create a stair between level 2 and level 3. Okay, so let me go into level 2 floor plan. Let's go and grab this stair. We have created the stair, if we go now in the section, you see that the stair doesn't automatically create cuts inside the floor. So this is the shaft things that we were discussing previously. So let's go back into level 2. And what you must do is create a shaft according to the stair, or basically by rectangle, which is better. According to the stair footprint, you create this thing here, which is a volume, which is invisible by default. But if you go, for example, in a 3D view, you see that it has already cut through the floor, and the shaft is this thing here. So you can decide for the shaft what is the base constraint. I would say that is level 1, so start from the ground floor without offset, and reaches the upper floor without offset. So it's basically cutting through all the floor where the stair exists. Actually, I should also create the stairs at the ground floor to get to the first floor. But anyway, I just wanted to point out this. So once you go back to the section, you will see that the connection between the stair and the floor, well, is not the prettiest things that you have seen in your life. Okay, so especially if you analyze this without line thickness, you see that it's not solved as connection. So even if you can create these elements automatically, you will have to further work on the graphic aspect of these connections here. And this is something that you must do in the old-fashioned CAD way, like switching back to something like AutoCAD or Rhino and whatever, and just deal with these connection details by hand. Okay, so Revit has some limitations itself, and this is something that you cannot solve in Revit. Imagine if you can solve this from Rhino Grasshopper, it's impossible. Okay, so stairs are problematic objects, and actually, as regards geometry gym tools, there is no way of defining a stair like a stair. Okay, so the only way that you can define a stair in Rhino Grasshopper and then send it to Rhino is through a particular component or node in Geometry Gym Revit tools. If you go inside GG Revit instance, you will find a particular thing which is called Revit Architectural Direct Shape. Okay, so whenever you have an element, a geometry or something that doesn't fall inside the standard architectural element categories like columns, floors, walls, beams, I don't know, windows or whatever, it is an architectural direct shape. So the way that you create stairs is using this architectural direct shape. Everything that comes before this component here is, once again, some kind of hard work in order to define the shape of these stairs. So I draw a line, which is basically the line that I was drawing in Revit. So I adopted exactly the same process. So you can see that basically it's no rocket science. Then I offsetted this curve, both sides. See, it's set to true in this case. So I have the width of the stair defined by this, which is half the width of the stair, so 1.5 meters width. And I also shattered the original line and created another offset curve. They look exactly the same, but these are continuous line from start to end point, while these are basically the steps, because I have shattered the initial line, dividing it into 15 steps. So if you take a look, for example, if I grab the endpoints, just to make it clearer, and take the endpoints of these lines, I get all the intermediate endpoints. So each segment here is independent from the other. So I can use them for defining the steps. Okay, so let's get rid of this preview. And actually what I have here is the lofts. So here you already have the steps. And before doing the loft, I simply moved each small line to the respective height. So you can see that we have these horizontal lines, each at the corresponding step level. And then I created the loft. And on the other hand, this continuous lines here. So there are no internal divisions here. These continuous lines have been used to define the rises. So you see, for example, that I took the continuous line, I divided the axis of this stair into the same amount of division as for creating the steps. I projected this point onto the side lines in order to create these lines. Now, these lines here are defining exactly the rises for our stair. Okay? Then I took this line and moved them with a series of displacement from 0 to the corresponding height in order to place each rise will have a height that basically in this case depends only on the amount of steps. There is no particular formula or expression behind this this stair. So it's not 2 times so it's 2 rises plus 1 step must be something like 60 something centimeters. So there is no formula in this case. It's just a number of division, but you can easily implement that formula here in Grasshopper in order to give this stair the proper inclination. And so I created this, which are the rises. So we have the rises, we have the steps. You see, it has no thickness. I joined all of these together into one single polysurface. And then I use this offset B-rep, which belongs to a component, a plugin, which is called Parakeet, which is basically a plugin that allows creating some nice patterns, okay? But it also has some surface utilities. And one of these surface utilities is offset B-rep. Okay, so it automatically creates the offset of the original surface with some thickness, 5 centimeter thickness. So I'm imagining some metal stair here, fancy stair here, not a solid concrete beam with the steps mounted. So this is once again the linear array of this element, and then you have the architectural direct shape, which is actually taking the geometry and giving some Revit-like properties. So first of all, type is set to stair. You see that inside the architectural geometry, the architectural direct shape, you have several types of objects. Everything that cannot be defined as a standard Revit element, you will find it here, together with some standard Revit elements, like columns, for example, can also be defined like a direct shape. Why? Because you can also create some fancy elements, some fancy geometry that you might want to use as columns. So if you want to create an architectural column, you could also define the shape of the column, not only the axis, because you cannot use the axis only like we did with columns. You must define the 3D column and plug it into geometry and say that that thing is a column, which is going to be considered only as an architectural element, not a structural element. Okay, so this is the only alternative that we have right now to define an architectural column. Okay, but pay attention if you want to define the architectural element like this with this direct shape, you must define the type. So once again, another value list that becomes mandatory to have in your Grasshopper template. So these are the stairs, and once again, this is an attempt to associate each instance of this stair to the actual level where it belongs. Okay. So let me also quickly show you what's the other thing that we have inside this stair, Revit stair creation. You see this other green thing here? This is the void or the shaft. So if you go here in Revit, besides these first things that we saw, there are also some generic component here, and there are also some generic component here at the end. And there are also some generic component in the Revit instances. So for example, you see these things here. And this instance here refers to exactly the cut geometry. So they are not exactly elements as we are used to know them. So they are not physically represented element like with a geometry. These are just cut geometry. So they create voids. And the reason why I'm using this is because I want to create a shaft passing through the floors. So this thing here works together with the floors. The reason why, if I, you see that this is actually showing just a preview of the box that is cutting through, cutting a hole through the floors. Okay, but if I go back here at the bottom and take a look at the floors that we're going to see later on, you see that this floor have this hole here. This hole is present because of this void here. So this void is created after the GG Revit floor, as you can see, but it affects the floor nevertheless with these holes here. Okay, so it's counterintuitive, this thing here, because normally in Grasshopper, when you plug something into something else, the last result that you get is that something else. But this time, the void is actually affecting this component here. And it's very easy because it's just an extrusion that depends from the actual volume of our stair. Actually, as the shaft is passing also, well, the stair is actually starting from this region here and enter this other region. So basically the volume of the stair would also affect the primary beam that we have here. And I don't want this to happen. So that's why I took this thing here and basically created a region intersection between the area of the stair, which is larger than this, as you can see, it ends up like here. And I also detected if this line here is affecting which region, you know. So the attempt is to keep things as parametric as possible. So I took the midpoint of this stair axis, evaluated in which region it was falling, and so I detected what was the region actually affected by this stair. I projected these at the ground floor, so you see that now we have the offset of this stair axis, like with the cap also. So cap type is set to 1, so linear, so it's closing the offset. So we have two regions, this one and the region affected by the stair, the main part of the stair. And so I created a region intersection, which is actually excluding the beam, the primary beam from this shaft. And I've used this region to create the extrusion and cap the extrusion and convert it into a void. So that's why you have this additional part here on top. It's just to better define the presence of the stair body and also to respect the primary beams. As for the secondary beams, you can change the orientation according to the points. So, for example, let's say that we have these stairs here, and I want to change the stairs. Instead of having the stairs here in the center region and oriented like horizontally, like here, I want them to be like from here. Well, actually, not from here to here, because there would be not enough space upstairs for, you know, getting off the stair. But eventually, for example, from here to here in this direction. Okay. So what do we do here? We take the original line, which is a custom line, set one line here, and say I want to start from here and get to here. So let's wait a second. You see the stairs already updated. The problem that we have right now is that if we go and take a look at the secondary beams, you see that we didn't get rid of these beams here. You see, they are still present. Okay, so we must, but we are back to normal here as regards this area. Okay, so one thing that I also have to recommend is from time to time refresh the script, the definition. So you go into solution and recompute or hit F5 in your keyboard. because sometimes these elements here, this component here, get updated, but not in real time, especially the floors. Okay, so just keep in mind that there is this trick here. Let's double check the void. You see that the void is already updated, and it's working perfectly, because if you take into account the primary beam, you see that it is created, but it respects the position of these primary beams here. So the void adapts perfectly. We should also double check that the floors already adapted. Yes, you see that there is this hole. The only problem that we have is with the orientation of our secondary beams. So in this case, for example, you see that things are basically working properly as regards the orientation, because we want the secondary beams to be oriented exactly like the stair inside this region. So we don't need to change the orientation. We need to get rid of these, well, eventually 1, 2, 3 secondary beams here. Why they are not updating? Because in this definition here, I only got rid of secondary beams in this direction. You see that this call pattern only works for the beams in this direction. If I want to get rid of these, I have to work with the other orientation, which is the vertical one. Let's say so. Okay. So if I want to do this, I must only also create this workflow here for this other set of lines that is not actually affected. So this is actually working properly. Eventually, if I'm not wrong, if I copy this, you see that this is connected to the first line. This is still connected to the first line, but I want to connect it to the second line. So let's see, because we still need to adapt this to the proper thing. You see, this is the loft surface. This is the wireframe. This is the joining of the wireframe. So we have the rectangle of the area of the stair. And now I am evaluating if I'm still using, well, actually all the lines. But no, because this is disconnected, you see? So that's the point. So I'm still using the first set of lines in order to evaluate the point on curve. Okay? So eventually I could switch to this. Let's see if this works. So the midpoint of this secondary beam, is it inside or outside? This is smaller than, and I don't want to see this. I want to see this. So no, it's not working. I think I have to split this into 2 separate workflows. Let me double check if it worked with the second. Oh yeah, I'm still seeing. Yeah, it was working. I was still seeing the frame, but the frame is not yet connected to this thing here. So yes, it is working. Let me double check if it works with the whole set of lines. So with one, no, it doesn't work with one set of lines because of the amount of things that we are considering, and also because if I plug this here, eventually I must also use the whole set of lines. Eventually, yeah, you see that now it works. So eventually, if I do this little change in the definition, this definition is going to work whatever, however I orient or place the stair. So just a quick check of this fact. Let's go into this line. Let's place the stair in another suitable place, like it will be something like from here to here. And yes, you see that we already got rid of the corresponding secondary beams in this area. Now, the other problem that we have is that if we do this, for example, in a region where the beams are oriented not along the stair axis, but cross section with respect to the longitudinal axis of the stair, we must change the orientation of the secondary beams. So, for example, if I define the stairs to start from here and reach, for example, here, we have a problem because these beams, these secondary beams, cannot be automatically deleted because their midpoint doesn't fall inside this region. So in this case, the only thing that we must do is go into the secondary beam orientation definition and eventually take this point out from this area. And you see that in this case, the beams are currently disappearing. Okay. Now, of course, you cannot distribute this point randomly like this. You must follow some order in order to give this structure the proper rigidity also and resistance to horizontal displacement, because you know that these orientation also affect the rigidity of the whole structure at this floor level. But nevertheless, this is something that I'm not taking into account in this at this point, at this stage. Okay, so we have a totally automatic workflow for placing the stairs in this thing. I understand this is pure geometry, but somehow I also wanted to give you a quick glimpse of what it means to keep everything connected inside this kind of complex definition in order to prepare everything for Revit, by the way. And so we have these lines here, and we can convert them into um, joists. In this case, for example, it's useless once you define, for example, these joists with one single step. It's useless to have two Revit framing component because you can simply take all of these and eventually let's deactivate this and eventually move all of them together and only activate one of these framing here. Okay, so you see that we already got the secondary beams properly defined.